Hello, everyone. Today we move into the interest rate term structure. This is a central topic in fixed income, and it matters both academically and practically because it sits behind bond pricing, risk measurement, and many trading decisions. To build this properly, we will go step by step. First, we will clarify what a yield curve is and why it is not the right object for discounting. Then, we will define zero coupon rates, also called spot rates, and explain why the curve of those rates is what we truly mean by the term structure. After that, we will see how spot rates are obtained in practice using bootstrapping, how interpolation helps fill missing maturities, and how forward rates naturally follow once spot rates exist. We will close with the main ideas used to explain why yield curves are upward sloping, downward sloping, or curved. A yield curve is a curve that relates maturities to yields. Here, yield means the yield to maturity of a bond, which you can think of as the internal rate of return that equates the bond's market price to the present value of its promised cash flows. The issue is that yield is not only driven by maturity. Yield also depends on coupon structure. Two bonds that mature at the same time can have different yields if their coupons are different. So even though the yield curve looks like a simple relationship between maturity and interest rates, it is not a clean discount curve. Conceptually, coupon is an extra dimension affecting the yield. This is why the yield curve is not the curve we want for discounting arbitrary cash flows. We want discount rates that depend only on maturity, not on whether a bond happens to pay a high coupon or a low coupon. This leads to the key concept, the zero coupon rate, also called the spot rate. From now on, keep this equivalence clear. Spot rate and zero coupon rate mean the same thing. A yield is different. A spot rate is the rate associated with a single cash flow at maturity with no intermediate payments. That is why it is clean. It is not affected by coupons. The curve that relates spot rates to maturities is called the term structure of interest rates. This is the curve you want for discounting, because it allows you to discount any cash flow at any maturity using the maturity matching spot rate. In practice, a published curve, such as the Tunisia clearing curve, is an example of a term structure curve. It is essentially spot rates plotted against maturities. If you have a stream of cash flows across multiple dates, you cannot discount them correctly using a yield curve, because yields are tied to particular coupon-bearing bonds. Instead, you discount each cash flow using the spot rate for that exact maturity. That is what turns the term structure into the universal tool for present value. At this point, the crucial question is where spot rates come from. In an ideal world, we would observe zero coupon bonds at every maturity. Then, inferring spot rates would be straightforward. You would use the price and face value of each zero coupon bond to back out the corresponding spot rate. But in many markets, we do not have zero coupon bonds for every maturity. Instead, we mostly observe coupon-bearing bonds. So we need a method to extract spot rates from coupon bond prices. That method is bootstrapping. Bootstrapping is a sequential construction technique. The intuition is that you build the curve piece by piece, like constructing a rope from connected segments. You cannot skip maturities because each longer bond pays coupons that depend on discounting at earlier maturities. You begin by selecting a set of liquid, reliable bonds across maturities, typically one bond per maturity you want on the curve. Then you write each bond's price as the present value of its cash flows discounted with spot rates. The first maturity is the easiest. In the simplified setting, the one-year bond behaves like a zero coupon structure because there are no intermediate coupon dates. So you can solve directly for the one-year spot rate. Then you move to the two-year bond. Its first coupon is discounted using the one-year spot rate you already found. The final two-year cash flow is discounted using the unknown two-year spot rate. Because the market price is known, you solve for that two-year spot rate. Then you repeat the same logic for 3 years, 4 years, and 5 years. Each step uses the spot rates you already discovered to isolate the next one. That is why the method is called bootstrapping. The 2-year spot rate depends on the 1-year spot rate. The 3-year spot rate depends on the first two, and so on. Once you have spot rates at key maturities, you may still need rates between them, such as at 4.5 years. A simple approach is linear interpolation, which assumes the rate moves smoothly between two known points. The interpolated rate should lie between the two surrounding rates. For maturities beyond your last observed point, a simple introductory assumption is flat extrapolation, meaning you keep the rate constant beyond the final maturity. Bootstrapping requires coverage across maturities. If you lack bonds in certain segments, you cannot build the curve reliably. In that case, you use models that impose a smooth curve shape and fit it to observed data. A common family here is Nelson-Siegel, and its extension Svensson. The intuition is that yield curve shapes can often be described by a few main drivers: a level effect, a slope effect, and a curvature effect, sometimes with an additional term for more complex bending. For this course, the key message is simply that bootstrapping is the clean construction method when data are sufficient, and curve-fitting models are used when data are sparse. Now we move to forward rates. Spot rates discount cash flows from maturity back to today. Forward rates, instead, describe the implied rate between two future dates, such as from year 1 to year 2. A spot rate is actually a special case of a forward rate, where the starting date is today. So, forward rates generalize the idea. The intuition behind computing forward rates is no arbitrage. Investing today for 2 years at the 2-year spot rate must give the same final value as investing for 1 year at the 1-year spot rate, and then investing from year 1 to year 2 at the forward rate. That equality pins down the forward rate. This also explains a result that can seem surprising at first. The forward rate between year 1 and year 2 can be higher than both the 1-year and 2-year spot rates when the spot curve slopes upward. This happens because the 2-year spot rate behaves like a geometric average of the 1-year spot rate and the forward rate. If the average is higher than the first component, the forward must be higher to pull the average upward. Finally, we ask why the term structure is not flat. Expectations theory says the curve reflects expectations of future interest rates. An upward slope signals rising expected rates, and a downward slope signals falling expected rates. Liquidity preference theory says investors prefer short maturities because they are more liquid and less exposed to interest rate risk. To convince investors to hold long maturities, markets must offer a premium, which tends to push long-term rates above short-term rates. Market segmentation theory says different investors concentrate in different maturity segments, so supply and demand in each segment can shape the curve independently. So, the story is consistent. Yield curves are useful summaries, but depend on coupons. Spot rates are clean discounting rates tied only to maturity. The curve of spot rates is the term structure. Bootstrapping constructs that curve from coupon-bearing bonds. Interpolation fills the gaps. Forward rates describe implied rates between future dates. And the shape of the curve reflects expectations, liquidity preferences, and market segmentation.